right? And I keep just checking one spot away, right? So that's all I need to do. How long will this take? ON, good. Okay, so this was the warm-up question, right? The warm-up question. The real question, of course, is here, which is when k is a given parameter. So k can be 5, k can be 6, and so on and so forth. Okay? So again, if you're stuck, then you would draw out maybe a sample, right? Let's say. So maybe we can build off our. Okay, again, the simplest way to solve this is to do what? Just merge sort it, right? Just merge sort, you know where it is and again. Okay, so let's try to do a little bit better, okay? So let's start off with the first element again, and let's just say k equals to 3. K equals to 3. So we know for k equals to 1, okay, let's start with k equals to 1. Now, if k equals to 1, I need to look at these two. We just solved that. What if k equals to 2? Where do I need to look? Let's index these. Okay? So, if k equals to 1, I need to look here. If k equals to 2, where do I need to look? How far do I need to look ahead? Does that... Right? I don't need to look all the way to the end. I just need to look here. For the first element. Just for the first element. Okay? Now, why is k equals to 3? Where do I have to look? Okay, it can only be in one of these positions, right? It can only be in one of these positions. Now, I know it's in this array, right? I know it's there. How do I get this? What do I need from this array? What do I need? Do I need the biggest element? I need the smallest. Okay, I need the smallest element. I'm going to look at the smallest element in this portion of the array. What data structure gives me the smallest element? Okay, and then you figure out the rest. All right. So problem 3, I was walking around and I was trying to see like where people got stuck. And problem 3 seemed like where people got stuck. So LCA is maybe something new, right? So we want the lowest common ancestor, LCA. So we want to know the node furthest from the root that it's an ancestor for both A and B. And remember, a node can be its own ancestor, right? So we give some examples. So in this case, let's say for 2 and 6, let's say you look at 2 and 6. The lowest common ancestor is 5. Okay? If the LCA for 12 and 2 is 10. Okay? Alright. So now we're going to find the LCA given two nodes, A and B, in a binary tree T. Now, it's very important to read the instructions carefully. Each node does not have a parent pointer. I've seen some solutions already that say that you've given a node, you traverse up the tree. You can't do that without the parent pointer. Okay? So, please read the instructions carefully. Your method should work on any binary tree and not binary search trees only. Okay? So I've seen some solutions where people have specified it's a binary search tree. It's not, okay? I mean, it's written here explicitly that it's any binary tree. Any binary tree means it doesn't have to follow the binary search tree properties. Okay. So if you are given this particular situation, it means that there's less order in this particular data structure because it's just a binary tree, right? It's not a binary search tree. So how might you go about this? So for me, I like to go back to the definition when I'm stuck, right? I go back to the definition of LCA, right? And I look at what it means to be an LCA. Now, if I'm an LCA, it means that I need to be at some point, let's say I'm traversing down from the root, right? I need to see that, let's say A or B is in my left subtree, and A and B is and the other element is in my right subtree. Then I know I'm an LCA, right? So I can figure out the algorithm from there by recursing downwards. So if let's say you are 2 and let's say 7, right? 10, for example, both of them are on the same side, right? So I'll go down and then I'll look at 5, and you look at 5 and you say, okay, one of them is on my left side and one of them on my right side. Okay? And that means I'm the lowest common ancestor. Okay? For this bucket. So this is when you have a binary tree, okay? And then you can figure out the way to solve it. I'm just giving you an idea. Now, for balanced binary search trees, there's a lot of order in your balanced binary search tree. Okay? So you can exploit that to some degree. Now I give you a hint here. Try traversing two different nodes. All right. So let's try that. So somebody give me two numbers. Somebody give me two numbers. Pick a number in this tree, of course. In this tree. You have to pick that one, right? Okay. All right. So 18 and 20. Let's try traversing to 18 and 20 from the root. So I traverse down to 20. I traverse down to 18. Okay. So let's just do some more. So this one's under here, and this one's under here. Alright? So, give me the other two numbers. Give me another two numbers. Give me one number from the tree. Just randomly pick. 3? Okay, give me another one. 7. Okay. So I go down to 3. I go down to 7. Okay. So for the previous case, let's say 18 and 20, which one is the lowest common ancestor? 18. Okay. For 3 and 7, where is the lowest common? The lowest common ancestor. Sorry. 5. Okay. Give me two more numbers. Let's say 2 and 6. Let's say. Okay. 2. Sorry. This. C. 2 and 6. Lowest common ancestor is 5. Now, if you keep drawing this, what's the pattern that emerges? What do you notice about the lowest common ancestor? What do you notice? Somebody said it. I heard somebody say it. But where? What is it?
The first parent node that diverges.
Yeah, it's the path where the first parent node that diverges, right? The path diverges. You see here, it splits at 5. 5 is the lowest common ancestor. It's the same at 12, at 18 as well, right? So it's where the path diverges, right? So figure out an algorithm that makes use of this observation. Okay. Yeah. Think about that. Do you think it works or doesn't work with the previous one, and why? Okay, that's important for you. Why? Right? After you can figure it out. Even though by the way the questions are structured, you can think about whether it can work in the previous ones. Okay. All right. Okay. So that's for quiz 2. I encourage you to go home, and so if you to think about the solutions and then work through. Okay. All right. So we'll be grading your quizzes. I think on Saturday. Yeah, I think Saturday is probably the day to do it. But then it's your turn to grade the course. Okay, so you grade me and you grade the TAs. So your feedback is very important. I said this before, and you do know that I tried to make the class, I changed the class in order to get you guys right as best as possible. So I'm going to post this on Piazza soon. The form is already up. Again, it's completely anonymous, and it'll take less than 5 minutes to complete. Please just submit one form, right? Or the stats will go crazy, so just submit one form. Also, your honest feedback is appreciated. So don't worry about hurting my feelings. Just say, okay, upset about something, just say, and then we'll try to accommodate whenever possible. Of course, I can't accommodate like strange requests. I've gotten some very strange requests before. I can't accommodate those. But in general, we try to help out. Okay, it should be class related. Okay. Mid-semester survey. Any questions? Okay. If there are no questions, you have covered a lot of stuff in the first part of the course, right? We've done ADTs, we've done, talked about sorting, search trees, and then all the way down to up to hash tables. So today we're going to move on to the second portion, right, which is a lot about graphs. Okay, we'll be talking about graphs for most of the second part of the semester. And today we'll be talking about just the basics. Okay, just the basics. I think how many of you people here have done graphs before? Have seen graphs before as a mathematical structure? Just check. So quite a portion. Okay. So today we'll be talking about graphs as a math structure and a data structure, and you should have seen some parts of these in earlier classes. If not, then for that there's revision. If not, then it's introduction. We talk about 2 ways to represent graphs in a computer, and then the differences. There are actually 3 major ways, but we covered it in video tutorial. And then we talked about modeling, so how we can examples of where graphs can be applied. So this is a problem, finding Herbert. Now, in previous incarnations of 2040, Herbert gets introduced to you earlier. Herbert is a robotic clown. I don't know, have you guys worked on any Herbert problems yet? No, you're right, it's a draw a GG. Yeah, I did do this last round. But previous semesters, people get seen Herbert robotic clown quite early. So Herbert's gone missing. He's in a sewer system. And the question is, how can we find Herbert? We can replace Herbert with whoever you like before he gets destroyed by an alligator. I say destroyed and it's a robot because I think eaten is quite gory. So, okay. The way to solve this is via graphs. Okay, so we're going to learn about how we can model this problem and solve it via graphs. Okay, so this is the idea. We're going to model the sewer system as a graph. Okay, each node is like a location. Each node is like a position, right, in the sewer system, and these connections are like the tunnels, okay, between each position. Okay. Each location can be, we call it a node or vertex, and each of these edges are links, right? These things connections between two nodes are called links or edges. Okay? And we can say that, okay, maybe Herbert's in this position, right? And that he's in one of the nodes, right? So that's this example of a sewer system, right? And Herbert is one of those places. Okay, so it can be fairly complicated. This is just a 3-node graph, but you can get it fairly complicated. Okay? Now here's a quick question. Which of these is not a graph? So you guys have no okay, there's this nodes and edges. Which of these is not a graph? A, B, C, D, C and B, all are graphs and not a graph. So let's do a quick poll, right? Let's do a quick poll. Which of these is not a graph? How many people think A is not a graph? Hopefully nobody. Okay. B? Lots of people. Okay. C? C, not a graph? D? Okay. So the right answer is B. B is not a graph. Okay. You can't have. Okay. Let's go back to the formal definition. Okay. And we'll see why. So graphs are a tuple of two sets. Okay. So B and E. Okay. These two are sets. Okay. This is the set of nodes. Okay. So imagine your nodes were labeled A, B, C. Let's say. So this will be a set of A, B, C. Alright? Now E is the set of edges. Okay, the set of edges are denoted is again a tuple or a tuple with V, let's say the nodes that are connected by this edge. Okay? So for example here A and B are connected. So in the set of edges E you would have A, B. Alright? A and C are connected, so you have A, C, and CB are connected, so you have CB. Okay. Indeed, we are going to start out with undirected graphs. Undirected graphs, you notice the edges have no direction. Okay, there's no direction. There's no direction this way or direction this way. We'll cover directed graphs at the end of today's section. Okay, but start with undirected graphs so that you can move in both directions. Okay, it doesn't matter. There's no direction to the edges. You can walk in this direction. You can walk in this direction. It doesn't matter. All right. Now from this definition, let's look back, and you can see that there is something wrong with B, right? There's something wrong with B because there are no nodes, right? There's no nodes. There's really no way to define an edge, right? Your edges are defined in terms of nodes. If there are no nodes, there's no way to define these edges, right? So that's something wrong with B. C is okay. C is okay because you can define a set of nodes. And E can be what? What can E be? The empty set, right? Or label like this, right? So it can be the empty set. All right. So C is fine, and D is our tree, and we'll learn later that actually trees are for graphs. Okay, there's a different way to define trees in terms of graphs. So this is a definition for a graph. There is a specialization called simple graphs. Okay, a simple graph is such that there are no self loops. Okay, so for every edge, VW, V cannot equals to W. So these two cannot be the same, right? V cannot equal to W. These two cannot be the same. All right. So that means that this visually, this graph here, you cannot have something like this. Okay, for a simple graph. Your graphs in general, this is allowed. Simple graph, this is not allowed. Okay. The other restriction is that for every two edges in the set, right, they cannot be the same. So that what this means is that there's only one edge per pair of nodes. You cannot have something like this. Okay, not allowed in simple graphs. Okay. A lot of the problems we're working on in this part of the semester, we'll be working with simple graphs, unless I specify otherwise. Okay, we'll be mainly looking at simple graphs, mainly, not always. Alright, so in simple graphs, remember, you're not allowed to have self loops, you're not allowed to have multiple edges between pairs of nodes. Okay, these are the two restrictions, and they'll make life easier for us. Okay. Alright, so is this a simple graph? What do you think? Is this a simple graph, yes or no? Yes. Why is yes? Because let's look. Are there any self loops? There are no self loops. Are there more than one edge per pair of nodes? More than one edge? No, right? So there's no more than one edge. So you'll find this is a simple graph. This is a simple graph, but it's not connected. Right? You notice that it's impossible to get to this part of the graph from some node here. Right? So we say that graph is connected if every pair of nodes, notice every pair of nodes is connected by a path. And a path, you can take as a very intuitive meaning that you can walk from one node to another. Okay? So for example, you want to get from this node to this node, right? There's a path connecting the two nodes, right? This one, or even this one, right? So it's a path connecting the nodes. So this graph, we say, has two connected components. Okay, this is a disconnected graph, but there are two connected components. So this is one connected component, because every node in this component can reach any other node in this component. Is likewise for this. This is another connected component. So if you start anywhere in this connected component, you can reach any other node in this component, right? But you may not be able to reach. You will not be able to reach nodes between these connected components. Okay. So if I start here, for example, I can't get here. I can't get to this part of the graph. Okay. So there are two separated components. This is a click. A click is called a complete graph. It's a complete graph. Okay. What it means is that it's fully connected. Okay. So every pair, all pairs are connected by edges. So you take any two nodes, there's an edge between them. Right? There's a click. So in a click, here's a question. In a click, what is the longest path from one node to another? One. Great. One. Right? All you need to do is to go one hop. Right? So if you start here, I can get to any other node just by via one edge. And it's likewise for all the other nodes. Okay, that's a special property of the clicks. So the diameter of a click is 1. This is the diameter. So let's formally define it. A diameter is a maximum distance between any two different nodes. Okay, so that's the diameter. So what is distance? What is distance? Distance is between two nodes. It's the length of the shortest path between the two nodes. Okay, so it's the maximum shortest path between any two different nodes. Okay, so that's. Oh, I think I gave the answer already. I pressed accidentally. Yeah. Okay. So let's look at this and look at the diameter of the graph on the left. Okay. So what is the diameter? Is it 1? I think I sort of showed the answer now. 2, 3. Yay! Everyone saw the answer. Okay. All right. So it's 3. All right. And you can see why. Right. We're going from the longest shortest path. So what you do is you check for every two different nodes, what is the shortest path between the two nodes. Okay? And then you take the maximum. Right? That's all. If you were to check, let's say you check this node, and this node, right? The shortest path is just 1. If you check this node and this node, the shortest path is just 2, and you keep doing this, right, systematically for every pair of nodes, and then you just take the volume lengths. Okay? And we'll learn about how to find shortest paths efficiently later in the semester. Here's a star. We saw a click, now we get a star. A star is one central node, right? All edges connect to the center, right? That's it. There's just one special center node, and then that connects to all the other nodes. That's it. So what's the diameter of a star? 2. Fantastic. It's 2, right? 2 because for every node, let's say the longest distance is through the center. So this is going to be, let's say, one shortest path. You find the shortest path for any of these will be 2. That's the maximum is 2. Okay. What is the degree? So this part of the lecture is a bit boring because we're going through a lot of definitions, but the definitions come in handy because or else we need a common vocabulary talk about the graph structures. If you don't have the common vocabulary, it's very hard to discuss what comes next. So we're starting with definitions, and then we use the definitions again and again so that will sink in. Okay? Alright, so the degree of node, what's the degree of a node? So the degree of node is the number of edges that are incident upon it. So let's just take an example. What is the degree of the central green node? So you just count how many edges are incident upon it. 1, 1, 2, 3, 4, 5, 6. Okay? That's it. It's just 6. Okay? So that's going to be your degree of the central node. So what happens if you have a self-loop? Remember I said no self-loop, but this is okay. Let's say I have a self-loop here. What is the degree of the central node? What do you think? 8. That's right, it's 8. Because loops are counted twice. Okay? Alright. There is the concepts of maximum degree and minimum degree. The maximum degree of a graph is the maximum degree among all its edges. So you just look for the vertex which has the maximum degree, and that's going to be the maximum degree of the graph. Okay? The minimum degree of the graph is, of course, the minimum degree of all its vertices. Right? So quite straightforward. So let's start using some of these. So this is a line and a cycle. So you can see a line is just how to say you have a line, very intuitive, right? You have all the nodes and they're just connected to one another in a linear fashion, right? For a cycle, it's slightly different from the line in that you form a cycle. You cannot have a not connected end like this. Okay, the ends are going to be connected. All right, so you have a cycle. Here's something to work out. So I'll give you, let's say, a couple of minutes. All right. So look to your friend next to you and find out what's the diameter and the maximum degree in terms of number of nodes for both the line as well as the cycle. Alright? So what is the diameter for a line, and what is the max degree, and what is the diameter and the max degree in terms of the number of nodes n. Okay? Give you a couple minutes. Let's go. Okay, time's up. So let's look at the line first and figure out its diameter. So what's the diameter of a line in terms of the nodes n? So if I have n nodes, what's the diameter of the line? N minus 1, good. So n minus 1, and you can draw a few examples of this, or you can just in general, right? So if you have n nodes, for example, you need n minus 1 edges to connect the lines, right? Okay. How about the max degree? What is the max degree of a line? 2, right? So you look at all your nodes and you say, what's the degree of this guy? This 1. What's the degree of this guy? 2. And all of the middle ones have a degree 2. Except for the one in the end, which is 1. So you take the maximum of these, which is 2. Alright. So let's move on to the cycle. So what is the diameter of a cycle? N over 2. Look at it, N over 2. So N over 2 because to get to where is the furthest node from every point? On the opposite side, right? So if you want to have the intuition, let's just draw a circle. Imagine there's like a infinite number of nodes and it's on the circle. You pick a point. Where's the furthest point? It's going to be on the opposite side, right? And the distance to that is going to be if this is n, then it's n over 2, right? Okay. And you can work it out for the discrete case. The max degree is, what's the max degree? 2. Okay. Look at every node, it's connected to 2 others, right? Okay, so you can do that. Alright. So, next question. Is this a valid graph? There's nothing wrong with the slide. Alright, there's actually nothing there. Okay, so just now we saw a situation where if you don't have nodes, but you have edges, that can't work, right? Now I say, I don't have nodes, I don't have edges. Is this a graph? So how many people think yes, this is a graph? How many people think no, this is not a graph? I don't know. So it turns out that all of them are correct. So there's a paper actually, it's called "Is the Null Graph a Pointless Concept?" From Harari and Michigan. The graph with no points and no lines is discussed critically. Arguments for and against its official existence as a graph are presented. This is accompanied by extensive survey of the literature. Paradoxical properties of the null graph are noted. No conclusion is reached. Okay, so let's do a quick terminology summary. Okay, guys, let's do a quick summary. Okay, so you now know what a graph is, at least a mathematical construct. Okay, it's just a tuple, right? Tuple with 2 sets, the set of nodes and the set of edges. All right. You know what the degree of a node is? The degree of a node is just the number of edges, right, connected to it. The diameter is the longest, shortest path between any 2 nodes. And then the connected graph is such that there's a path between any 2 nodes. A click is a fully connected graph. A line graph is a line. A star is a central node connected to all the other nodes. Okay, so these are some basic terminology. So if I ever say a star in the future, you know what I mean. If I say, a click, you also know what I mean. Okay. All right. So let's move on to some fun stuff, which is examples of real-world graphs. Okay, examples of real-world graphs. So you know of many. You have encountered many of them throughout your life. For example, social network. A social network is a graph of friends, right? Let's say sometimes frenemies, but friends. This is an example of another graph, which is your MRT network or transportation network. This is some work I did as a postdoc. This is a CBD area in Singapore actually, and we're trying to model cars moving around between parts of the CBD. You see the yellow lines, the orange lines, those are autonomous vehicles. So we're doing autonomous vehicles research, and we wanted to ask, how many autonomous vehicles do you need to service, let's say, people in the CBD area, right? So every time you see yellow lines like flowing, that's a bunch of autonomous vehicles moving from one part of the CBD to another. And the blue lines are like all the other cars. So you can model this. The whole structure of this simulation was a network, actually. All right, and you can read about it. It's called SimMobility. There's also communication networks. So you have a bunch of satellites up there, and also that feed Netflix to us and all the other fun data. So that's communication network. Computer networks are one fundamental part. Right, they are called networks for the sake, so they're a giant graph. This is a drawing of, if I'm not mistaken, it was the internet back in 2005, so quite a while ago, where each node is just two reachable nodes, right? And if you see there's a bit of thickness, the distance between any 2 nodes here was how long it took to reach that node. Okay, the delay, the ping delay between the 2 nodes. All right, so they're delayed now here. And you can see each one of these points is actually an IP address. This is a giant graph, and you can model it that way. Here's a fun one. These are game graphs. So how many people heard of this AlphaGo competition? Anyone hear about this? Yeah, it was pretty cool, right? So was it a couple years back that a computer beat the world champion, right? At the game of Go. The game of Go is special because for a long time we thought that, at least us in AI, we thought that okay, this is going to be very hard to solve. because the state space of Go is huge, right? It's an old game that people in Asia have played for centuries maybe. But for computers, we decided that this is going to be really, really hard, at least to beat a human being. And it turns out, well, human beings are not so great, and computers can do better. Okay, so these are game graphs. So let's talk about game graphs. I can't do Go because Go is very, very hard. But I can talk about the simpler game graph, which is called a sliding puzzle. So how many people have played this before? You played this before? Have you played this before? Okay. So if you haven't played this before, what you have is you have these tiles, right, in this square. And what you're supposed to do is just get the tiles arranged in order, right? So you want 1 here, 2, 3, 4, in this kind of order, right? Very often it's a picture or something, and you're trying to arrange it so that the picture emerges, right? So that's how the game is structured. So I'm going to show you a simple game graph. In this game graph, there are only 9 spots, okay? And this is the empty spot, okay? So you can move tiles. As in, for example, I can move the tile 6 down, or I can move 2 to the side, right? So I can just move the tile around. So let's just say you want to solve this line puzzle, and the way to do it is to get 1 in this position. Okay, I only get 1 here. So I can't move. I'm not allowed to pick up the tile and put it back in, although some people do that. That's cheating. So I'm only allowed to move tiles around. Okay, so that I can get 1 to that position. So what can I do? How can I start moving it around? Well, maybe I'll move 6 down, and I'll move 7 here, and I'll move 5. Okay, that's good. I'll move 1 up. I move 3 to the side. I move 4 down, and put 1 in its correct spot. Okay, so that's one possible solution to get 1 to that place. Okay, then I keep carrying on until I solve the problem. Okay, so we can see that each state of this game can be represented as a node in a graph. Okay, so each state, like this state to this state, right? This state, this whole thing is a node in the graph. Okay, and how we are going to build this graph is to connect up nodes that you can get from one node to the other via one slide. Okay, so essentially, if you look this, I moved 1 this way, and then these are connect, and I can move 1 this way, and this way. Right? So these are undirected graph. These two are not connected because I can't get from this state to this state just via one move. Okay, I need to go via this move followed by this move followed by this move to get from this state to this state. Okay, so here, for example, I move the 3, I move the 4, and I move the 1. That's the only way I can get from that state to that state. Okay, I can't move directly through a series of other states in order to get there. Okay, so this is our setup. Okay, this is our graph of the game where each node is a state of the puzzle, and then the edges are just connecting 2 states if they differ only by 1 node. Okay, so the number of nodes is very large. It's very, very large because each one of these states you can think of as a permutation of the 9 tiles, right? Where the empty tiles is considered tiles, so there are 9 factorial, which is about 362,000. And the number of edges is smaller than 4 times the number of nodes. Why is that? Why is it 4 times? Very good. So the maximum you can move is, let's say you can move this here, move this here, move this here, move this here, right? So there are 4 possible spaces, unless you're in the corner. If you're in a corner, you can't really do that, right? The corner you have 2. So the maximum is 4 times n factorial, okay? And this is what that is, right? So 1 million, 1.4 million. So it's a relatively large graph. Okay. Now here's the question. So I've represented the game like this, right? In terms of nodes and edges. I have some initial scrambled state. Okay, this is the start of the game, and I want to get to this end state. Okay, I want to get to the end state. So the question is, this is most related to which concept that we've covered before? Is it related to the diameter, the degree, the click, the connectedness, or I guess B? So what do you think? Is it related to the diameter? Degree? Click? Connectedness? I guess B. So the right answer is diameter, actually. So why diameter? So the number of moves required to solve this puzzle, why is it related to the diameter? So if I want to get from one state to the other, there is a path, right, connecting me from one state to another. Now I want to do it efficiently, so do I want the longest path? No, I want the shortest path, right? So if I want to start from any of the states, and I want to reach this final game state, right? So what's that related to? Possibly, it's related to the longest of all the focus points, right? Which is the diameter. So the number of moves to solve the puzzle must be less or equal to the diameter, right? And I will just explain why. It's just because you can start from any possible state, right? So it must be less or equal to the diameter. Here's another game which is quite popular. It's called the Rubik's Cube. How many people here play the Rubik's? You have a Rubik's Cube? Last year I did this and somebody came brought out a Rubik's Cube from his bag. It was amazing. So does anybody have a Rubik's Cube today? I should just buy one and use it for class. Okay, so this is a simple Rubik's Cube. This is a 2x2x2. Right? 2x2x2. So it's a smaller Rubik's Cube than maybe the one you've seen, which is 3x3x3. So this is a video. Pay attention. This is quite cool. This is a guy who's trying to solve the Rubik's Cube, 2x2x2 Rubik's Cube. So he's looking at it, he puts it down, and he's done. So this is the world champion for 2x2x2 Rubik's Cube. He solves it within half a second. This is like insane, right? So you want to see that again? Because his answer there just says, okay, this is Rubik's Cube. First time looking at this configuration, I put it down. Okay. I don't even see his fingers. Yeah, okay. Amazing dexterity. That's amazing. Okay. So that's super impressive. So let's talk about how we can solve. I can't solve it like him. My fingers just don't work that way. But maybe we can solve it using computers. Okay. So we're going to build a configuration graph. Again, it's very similar to the sliding puzzle, where each node is a game state, the state of the Rubik's Cube. Okay. And then each edge is then a basic move. A basic move is we're going to label it as either a 90-degree turn, so just 90 degrees, or 180 degrees. Okay, so you just turn on the section. You guys know how Rubik's Cube works, right? So you just turn it 180 degrees. So the puzzle, of course, you can model it as given some initial state in this graph, you want to go to the solved state. The solved state is a unique node in the graph. Okay, so you want to get that. So you want to find a path to that node. Okay. So the question is how many vertices? It's very, very large, much larger than this slide puzzle. Okay. There are 8 factorial number of cubelets. Right? So 8 is the number of cubelets. Okay, 1, 2, 3, 4, 5, 6, 7, 8, right? 8 cubelets. And they can be in one of the 8 positions. Right? So that's going to be 8 factorial. And then we have each of the 8 cubelets can be in one of 3 different orientations because it can have different facings, right? It can either face this way, face the other way, or face up, let's say. So there are 3 possible facings in each of the cubelets. You can reduce this a little bit by considering symmetry. So why can you consider symmetry? It's because if you have the cube in the state, if I rotate it, it's still the same game state, right? I haven't increased the number of the game. I haven't changed the state of the world. I've just rotated it by somehow, but it's still the same cube. Right? I haven't actually rotated it or anything. I just rotate the whole cube. Alright, so if you consider symmetry, then you can reduce it by 1 on this side, right? And here, right? So you basically what you're doing is you're fixing the position of one of the cubes. Alright, so that will be 7 factorial times 3 about 7. This should be 7 here, right? And that will give you about 11 million. Okay, so if you have this configuration graph, then you have some initial state, and I want to get some to one winning state. And you can see all the you can have sets, right, of all the nodes that you can reach within one move, and all those that you can reach within 2 moves, and so on and so forth, right? And you can see the number of states that you can reach as you go along. So the question is this, what's the diameter of a 3x3x3 Rubik's Cube? Okay, this is a bigger one, so we looked at 2x2x2. Here's a 3x3x3. The configuration graph has 43 quintillion vertices. Quintillion is like, I can't remember, 16 zeros or something like that. Okay? It turns out that the diameter is 20. Right? The diameter is 20. In fact, God's number for the 3x3x3 Rubik's Cube is 20. You know what God's number is? God's number is, if you were God playing the Rubik's Cube, you know the optimal solution. It takes 20 moves basically. Yeah. A maximum 20 moves to reach a particular solution. That's God's number. Okay? A maximum 20 moves to reach a particular solution. So starting from any state, you need only 20 moves. Okay? To reach a particular solution. So this took 35 CPU years of computation. it was crazy, right? Coding is up. You can look at this website, cube20.org. I'll show you. There you go. So this is a website you can find. I think it was done by Google, who solved this problem using a really complex program. And you can see that people have been working on this for some time. In the 80s, they discovered that the lower bound for God's number was 18, the upper bound was 52. There was a big gap between there, a gap of 34. But that gap was slowly reduced over time until 2010, when they showed that the lower bound upper bound basically matched, and that was 20. Okay. So this is your quintillion number, and you can read more about this little program if you want, okay, and how they solve this particular problem. Okay, so that's the Rubik's Cube. How about if you have some crazy ass Rubik's Cube, which is an n by n by n cube, let's say 22 by 22 by 22. What do you think the diameter is? So I won't expect you to know, but the diameter is n squared divided by log n, and there's a paper on that from MIT and Waterloo. So you can read about it if you were interested, and it talks about how actually it's big theta of n squared over log n. Okay, that's the diameter of the configuration space. Okay, so let's talk about, we've covered how to represent graph, and you see now some examples of how you can use graphs to represent real world problems and games. That's it. So here we have the mathematical definition of a graph, right? And you may have seen this from 1231, let's say. But how about in the computer? How do you represent this in the computer? So I'm going to talk about two different ways today. The first is called adjacency list. Okay, this structure may look a bit familiar, I think, right? So what does this look like? It looks like a hash table, right? It looks like a hash table. So the concept as well is very simple. What we're going to do is that for each of these nodes, right, we have for each of the nodes, we are going to represent, we're going to install a linked list of who this node connects to. Okay, so for example, node A. Node A is connected to two nodes, E and F. And so there's a linked list here representing E and AE and AF. Okay. Likewise, B is connected to three nodes. So B here is connected to BC, so it's BC is here, BD is here, and BD is here. Alright, so this is a simple adjacency list. There is also adjacency matrix. Okay, adjacency matrix, instead of having a list like this, imagine if this was arrays now, then you're going to have a matrix. Right? Adjacency matrix is very simple. It's zero anywhere other than where the two nodes are connected. So for example, this is A, B, C, D, these are the nodes. These are the nodes. If A and E are connected, then there's a 1 here. If A and F are connected, there's a 1 here. Alright, so it's very simple kind of setup. Alright, so everyone's clear on the adjacency matrix, adjacency list? Okay, so adjacency matrix is just one if the edge is in the set. Okay, set E. And there is a nice property of this, in that if you take A and you square it, then you have all the lengths of path 2. Okay, so I encourage you to try this, right? A squared means that you guys have done matrix multiplication before, right? So you have two matrices, you know how to multiply them. So let's just say, no sub edges, sorry. No sub edges. Let's say, and then you multiply it together. So what do you do when you multiply matrices together? Take the row, multiply, right? You take these two elements, sum together, plus these two elements, sum together, right? Keep going from there. Okay, so what do you do? In this case, what do you get? The first element. Second element? So this one, right? This one is 0. Okay, you're right. Okay, how about the next one? And the next one? Right, so you just matrix multiply, right? So that's going to give you a square, and A squared will give you your length 2 paths, and you can, sorry, give me a second. So if you want to find out if C and D are two hot neighbors, right, meaning that it takes basically 2 steps to get there, then you just multiply together, right, how to show, and it's 1 if basically ACX for some x, right, equals to AXD. It means they're two hot neighbors. right? That's what it means. So you can generalize this a little bit. You can generalize to length 3 paths, you can generalize to length 4 paths, or any length k paths. Now it turns out that if you generalize to A infinity, you get Google PageRank, right? Google works like this, all right? So what they do is that they basically imagine, let's see, how do I describe this in more intuitive terms? So in Google's PageRank algorithm, a graph basically represents links between edges. In fact, it represents the probability that you actually go to that particular website from a given website. Okay. Then what you can do is that you can compute the rank, right, or rather the importance of a particular website using matrix calculations. All right. It is beyond the scope of CS2040, but I thought it would be fun. All right. So for graphs, right, all you need to do is to every time you power it, you get some interpretation, a clear interpretation there. It turns out that this interpretation can be used to power your search engines, for example. Right? This is related to, in fact, the eigenvalue problem. Some people remember the eigenvalue problem from the algebra. Okay, so it's related to the eigenvalue problem. You don't have to know, but just if you are curious, then I would suggest you Google it. Okay. All right. So let's get back to CS2040S. Now, for a cycle, which representation is more efficient? So let's put this on poll everywhere, right? Let's see whether we've really understood the two different representations, the AJCC list and the AJCC matrix. Okay. So for a cycle, which representation do you think is more memory efficient? Right? We care only about asymptotically here, so I don't care about the precise how much a byte takes. Like just asymptotically in the number of nodes. All right. So do you think that it is it the AJCC list or the AJCC matrix? Let me put that second. Okay. So which do you think is more efficient for a cycle? Memory efficient, by the way, not time efficient, so memory efficient. Okay, so I'll just give you a moment. Let's think about this. Okay, so it looks like most people put in AJCC list, a smaller number put in AJCC matrix. Some say it's the same, and then others are still thinking about the Rubik's Cube. Okay, so let's have a look. So for AJCC list, right, if you look at it this way, that each node is just connected to one other, right, for a cycle, right, for a cycle, then it becomes OV, right? In general, it is OV plus E because you have your V here and then your E here, right? So in general, it's OV plus E. But for a cycle, since every node is just connected to two others for a cycle, so then that's going to be restricted to 2 times V. So this is 2 times V, so it's OV, right? So V plus 2 times E, 2 times V is 3V. So on the order of OV. How about AJCC matrix? Now, AJCC matrix is not great because for this particular situation, because you need to, regardless of how many edges are actually active, right? They actually exist. You still have to represent zeros. You have to still represent the edges that don't exist here as zeros. Okay. So this is quite wasteful, memory-wise. In this, and you can see this in terms of the total required in general, and also for a cycle. It doesn't change, right? Not like the AJCC list. It doesn't change for specific graph structure. Right? It's always OV squared because you need to represent this matrix, right? There's always 1 to 0, you need to represent it in this way. So the right answer here is AJCC list, okay, which is more memory efficient for a cycle. How about for a click? So for click, let's put this again on to everywhere. So which again is more memory efficient? Is it going to be the AJCC list or the AJCC matrix for a click? Okay, So again, break it down and think about the structure, okay, the structure, and try to figure out how many, in terms of big O at least, asymptotically, which one is more efficient. Okay, so we have 22. Most people put same. Some people have put adjacency matrix, and a smaller number put adjacency list, and some people are saying which is correct. Okay, so the right answer is same, at least asymptotically, right? And you can see that when you think about how this is structured, right? So for a cycle is OB, but for click, right, you need to represent how each edge is connected to all the others. Right? So that means you have B squared edges, right? The order of B squared edges. So that's not going to be great for you because that means that you have to represent B squared on the order of B squared edges in your adjacency list, right? Adjacency matrix, it doesn't matter, it's always just B squared, right? So at least asymptotically they are the same. Asymptotically they're the same. But in practice, they can differ quite a bit, right? So you know that for a adjacency matrix, for example, if you represent it efficiently, you don't need like a whole floating point number to represent 0 or 1, right? You can represent quite effectively using a bit, that's it, you need to. So it can be quite memory efficient in that way. Versus a adjacency list, right? You need to have references, and references will be quite expensive. Okay, you need this more complicated structure, and that comes with some overhead. Alright? So just a general guideline in practice, if your graph is very dense, try using adjacency matrix. If your graph is sparse, then adjacency list will be more effective, right? There's another structure called the H list, which we will cover later, all right? But these two are the primary ones. Okay. All right. So remember to ask, right? If you're going to use these forms as representations, right? It basically is, is the graph dense or sparse? And the next thing you need to ask yourself is what kind of queries do you need for your particular operations? So let's just give an example. Let's say I work on Facebook, let's say, or I work for Facebook, and I have this giant social network, right? I have this giant social network. And I need to do some things on Facebook website. So you can click, for example, you click friends, and then it gives you a list of all your friends, right? It gives you a list of all your friends. So I want to be able to do this operation very effectively. So what representation do you think is more effective for oh, sorry. So this is, I jumped ahead, sorry. This query is are Alice and Bob as friends? So essentially I give two people, let's say I randomly pick two people in this class, one over there, one over there, and I ask are these two friends on my social network? Okay? So which representation gives you a faster, allows you to query whether two people or two nodes are connected or two people are friends more effectively? Adjacency list, adjacency matrix, the same, or I have no friends, set face. So let's check. So remember, think about the representations and how you might execute this operation. Oh, so sad. I don't believe that's the largest one. It's growing. Oh my god, 63% of you responded. So sad. Okay. So the right answer is I have no friends. Sad face. No. Okay, the right answer is adjacency matrix, alright, as you may have guessed. And why is it the adjacency matrix? The adjacency matrix, because for matrix, all you need to do is just check, right, A, I, J, and just see whether that's a 1. If that's a 1, that's a very fast operation to do, right? So you just check that's a 1. If that's a 1, then you return true. Yes, they are friends. Okay, so very fast, like go on average. What if you want to do friend enumeration? So this was the one I was talking about before because I'm confused. Is you go on Facebook, you click friends, and Facebook lists down all your friends, right? There. Yeah, but if in a special case where you have no friends, then of course that's easy. But if you have friends, then Facebook has to do some work, right? So the question is, which representation is faster for this kind of query? Do you think the adjacency list, the adjacency matrix is the same, or not sure? Okay, again, this is friend enumeration, so I want to basically I go there, I say, okay, who are my friends, and then it gives me a list of, I don't know, 0 people. Okay, so I think most of you are saying adjacency list. People here saying the You guys are just messing with me, is it? I said I'll wait till 20 and it stops at 18. Okay, 18 it is. 19, okay. So, which representation is faster for friend enumeration? So if you answer adjacency list, you are right. And why is that? So for adjacency list, all you need to do is to go to the node that you're querying, right? And then you just run through the list, right? You attach the list, make list, and you can enumerate all the friends very effectively, right? If you have a matrix, right? What happens is that you have to enumerate one by one, regardless. Now, this is I would say in practice, right? When the number of edges, the maximum degree, is quite low. So for example, there are many nodes in the Facebook social website, but you can think of the effective degree is quite low. Although there are 4.5 billion people in the world, how many people on Facebook? A billion, let's say. You're not connected to all 1 billion people, right? You're connected to, I don't know. Some people, you have no friends, so 0. But if you had friends, then I think the average number of Facebook may be 100, 200, let's just say. Okay? So in that case, it's very small relative to the size of it. So B squared is very large, but the number of friends that you have is actually quite low. Alright? So adjacency list in this particular case would be much more effective. Alright, so you want to think about the trade-offs in terms of represent how much memory you need, but also how fast you can do certain operations. Right? And the types of operations you require depends on your application. Okay, and we'll talk about how we can do certain more advanced operations as well. So we covered about undirected graphs. Let's just take a quick view at directed graphs. So directed graphs are when the edges actually have a certain direction. Okay, like look at this one, right? So it means that actually intuitively, if you have, let's say, a path, they're like our roads on our, let's say, on the street, right? You can only go in one direction. There are one-way streets, right? So you can only go in one direction. You can't go both ways, right? So directed graphs allow you to represent these kind of situations where you can maybe flow in only one direction. Okay. Now, the structure is similar. So we also have a couple of two sets, B and E, where B is a set of nodes and E is a set of edges. But for the edges, the order matters. Okay? The order matters. If I write VW, it means that there's an edge pointing from V to W. So let's just say I have a graph here, ABC. Okay? I can't write, let's say, AB. Let's see this. Okay? I cannot write AB. Right? This is wrong. Because the edge flows from B to A. So the right order is BA. That's also why this is a tuple or ordered set and not a set. Right? A set there's no ordering. Okay? Here order matters, and so each one of these you have an origin node and a target node. Okay? So keep that in mind, right? And you can write out the other edges in this set. Okay, so we have to modify our definitions a little bit based on this concept of directedness now. There is now an in degree and an out degree. Alright, and it's very intuitive. The in degree is just the number of incoming edges. So all the arrows that are pointing to me, that's my in degree. Out degree is just the number of nodes I'm pointing to. Okay, so that's my out degree. So very simple. For this node, for example, let's call it A. It has an out degree of 3. 1, 2, 3. What is an in degree? 0. Right? It has no nodes connecting to it. All right. And for let's say this one, the in degree is 2, 1, 2, and the out degree is 1. So very simple. So again, we can represent a directed graph in a computer, right? In the adjacency, you can represent either as adjacency list or adjacency matrix. Okay, very similar to the cases that we talked before, but there's going to be a little bit of differences. So let's talk about that. So in an undirected graph, you notice that E here, A. Let's see, where is it? A. Node A has E in its list, right? This node is connected here. E also has A in its list because the node is undirected, right? You can flow both ways. For a directed graph, you only represent the outgoing edges. You don't have to represent the incoming edges. Okay, so every node, for example A, is connected this direction to E, this direction to F. A is connected to E, so exists in A's list, but A does not exist in E's list. Okay, notice there's no A over on this list here because A this is an outgoing edge from A to E. Okay. So we only represent outgoing edges. Now let's talk about adjacency matrix. Adjacency matrix is again very similar in that we also always just represent we represent an edge, right? Only if A, B, W, and B is the row. This is a column. Okay, so this is my row. This is my column. A, B, W is 1 if and only if B, W is in E. So that means this edge connects from B to W, right, in this direction. So A connecting to E, right, means that A with row A and column E should be 1 and not the other way around, right? So if you look at E1, EA, that's a 0 over here. Right? So keep that in mind when you're talking about directed graphs, the adjacency matrix. You have to look in the correct row and column. Okay? If you look at the wrong one, you can misunderstand what the graph structure is. Okay? So remember, you look row first and then column. If there's a 1, it means that there's an edge pointing from whatever the row ID is to the column ID. Alright, so that's our adjacency matrix. You can use adjacency matrix to represent lots of different things. For example, friendships. The question is, are friendships always bi-directional? So if you know some people, your age represents your friendship, then on Facebook, yes. Basically, your friends on Facebook, right? It must be that if you are friends with them, they are friends with you. It's always bi-directional, okay, on Facebook. But on Google Plus, before when Google Plus was still live, this was not the case. You can follow somebody, but the person not necessarily follow you, right? So Google Plus is shutting down. So Google Plus has shut down actually. So maybe friendships are bi-directional. I don't know. Okay, so that's one thing to think about. The other thing which is kind of fun are these K-grams. Okay, so there's a field called text generation. Because basically you generate text. So you can imagine if you're writing on words, you're generating one letter after another. Okay, there's something called Markov text generation, where each node is a K-gram. So what's a K-gram? A K-gram is a continuous sequence of K items, right? So syllables, letters, or words. Here we represent. Let's say we have letters, okay? And each letter here is about 5. Each node is a 5 gram. Okay, so there are 5 letters, right? And an edge is such that one K-gram follows another. So if you have compute here, the next letter is this is the next 5 gram. This is the next 5 gram, which is compute. And then you can go up. You can connect to 2 possible things. It's either compute or you can imagine computation later on. So this is an example of how you can represent, let's say, text generation. From text generation is a graph. Okay, you're moving from, let's say, some part of the word to another part of the word. Okay, and in this case, it's a sliding wheel. All right. When you represent things in this way, you can actually use these to generate text. What you would do is you would do sampling. All right. Let's say you start at this node. Okay, and then there's only probability of one to go here, so you move to the next one. So it's always going to be compute. But over here, maybe you look at the frequency of words that appear, and you say, oh, this happens with quite even, let's say 0.5, 0.5. So I'm going to flip a coin and say, oh, with its heads, I'm going to do computer, and if it's tails, I'm going to do compute. Okay? So that's an example of how you can generate new text going forward. Right? Small way. So you can do this to generate papers. You can do this to generate homework papers, for example. We use it to generate computer science papers. This is software that you can download. Actually, I tried to download it. I couldn't seem to download it anymore, so maybe it's already offline. It's called SciGen. And you can generate CS papers. So what they did was they basically built a context-free grammar, slightly different from the Markov system that we talked about, but not too dissimilar. And they used that to generate text. Okay, the data for that came from a set of computer science papers. And so this is an example of paper they generated, and conference actually accepted it. That just tells you the state of peer review. So the interesting thing is that this software generates quite syntactically it looks correct, but semantically it's just dumb, right? He has no idea of semantics, but he has a pretty good idea of syntax, right? So if you read the syntax, it makes sense. Like many physicists would agree that had it not for congestion control, the evaluation of web browsers might never have occurred. But it's totally meaningless, right? It doesn't make sense. You can continue on and read this. You can download this paper actually. But none of this makes sense, right? This syntax, it looks good, but semantically it's still. I just want to clarify that this paper was accepted as a non-peer review paper, and there was a debate back and forth. You can read about the controversy online. Peer review is something computer scientists and other people talk about as well. Sometimes that peer review leads to bad papers being accepted and published, right? So we always want good peer review. And when you have no peer review, then you can get papers like this accepted, which is not great, right? It's totally meaningless. Okay, so we are at the end of today's lecture. I now know how to represent graphs, both mathematically as well as in a computer, which is list and its matrix. And then we have seen some examples of how we can use graphs to model problems, like sine puzzle, or Rubik's cube, or later on, like by connecting words together, right? You might have said, well, we haven't solved the problem that we started out with, is finding Herbert. So Herbert can stay in the sewer for a while. We'll save him next week. When we talk about how to model things a bit more, and also how to search on graphs. Okay, so when we come back, we talk about breadth first search and depth first search. Okay, so I'll see you guys next week. If you have any questions, just raise your hand or leave it out here for a while. Okay, so see you next week.